In this lecture, I will discuss solution to some specific problems from the exercise of chapter number 6 of the textbook of Mechanics of Material by Beer and Johnson. The title of the chapter is Shearing Stresses in Beams and Thin Wall Members. The first problem is from chapter is 6.1 from the exercise. 3 full-size 50 into 100 mm boards are nailed together to form a beam that is subjected to a vertical shear force of 1500 Newton. So vertical shear force is given to us. There are three full-size boards, wooden boards here. 1, 2, 3. They are nailed together using nails. Knowing that the allowable shearing force in each nail is 400 Newton. So in each of the nail, allowable shearing force is 400 Newton. So it means the horizontal force in the nail, the force will always be in the horizontal direction, either this one or this one. So this is allowable one is either you call it horizontal shear force or denote with H or F. It is 400 Newton. Determine the largest longitudinal spacing S. We have to find S, longitudinal horizontal spacing. So it means it is horizontal force in the direction of nails. We have to find S that can be used between each pair of nails. Okay. As we know that horizontal force is equal to Q into S. But here in the cross section, if we see there are two nails passing through each board, so the force will be divided by 2. The force will be divided by 2. So it means, or you can say, we need double force in each. We need double force, or if it will be divided by 2 into each nail. We will have H, force H. Okay. We have to calculate S. For S, we need horizontal force H, which is given to us. It is 400 Newton. And we need Q. Q is unknown. If we find Q, we can find S. Q is equal to V capital Q divided by I. Small q is shear flow. And greater Q, the capital Q is first moment of area. V is given to us. So we need to find capital Q and I. I can be found, it is a rectangular cross section. It is very easy to find I for this cross section. It is 100 into 150 cube divided by 12. Capital Q, we have to find capital Q. Remember that the first moment of area in such kind of problem is always found for the area above the horizontal shear force. Horizontal shear force exists on this line. It is at the interface of the two wooden boards, and the force exists in the nails. So area above this line where the horizontal shear force exists, this area. Or if we consider this one, the bottom plane, so we have to consider this area. So any of these two areas can be used. So I will use this formula A y dash. A is area of the plane, cross-sectional area, which is highlighted here, and y dash is distance of its centroid from the centroid of the cross-section. So I will move towards the solution. Problem 6.1. There are 3 planks, so we need to consider this area. It has a distance of y dash from the centroid of the area. These distances are given to us. Each one is 50 mm. First, I is equal to width into total height cube divided by 12. So this will come out to be 2.812 into 10 power minus 3. It will be 10 power 7 millimeter power 4. Or if we want to convert it into meter power 4, so it will be 2.812 into 10 power minus 5 meter power 4. Okay. To find Q is equal to A y dash. A is the area of this highlighted cross section. So it is 100 because horizontal shear force exists on this interface. So the area above this horizontal interface is 100 into 50, and y dash is distance between the centroid of the total cross section till the centroid of this area. So it will be 50 in this case. Okay, so we have to calculate this as well. This will be 100 multiplied by 50 multiplied by 50. So it becomes 2.5 to 10 power 5 millimeter cube, or if we want to convert it into meter cube, so it will be 2.5 into 10 power minus 4 meter cube. 1 millimeter is 10 power minus 3 meters, so 1 millimeter cube is equal to 10 power minus 9 meter cube. Okay, shear flow is equal to VQ over I. V is given to us, it is 1500 newtons. Q is 2.5 into 10 power minus 4, and I is equal to 2.812 into 10 power minus 5. Okay, so Q becomes 133.33 Newton per meter. Now, as we know that horizontal force, 2 times horizontal force is equal to Q into S. 2 means we have 2 nails in each plank here. So we need double force. 2H is equal to Q into S, or S is equal to 2H over Q. H is given to us, it is 400 newtons, and Q has been calculated. So S becomes 0.06 meters, or if you want to convert it into millimeters, it will be 60 millimeters. So it was very easy to understand. If we know this expression, H is equal to Q into S, but we have 2 nails, so there will be double force, or the force will be divided by 2 into each nail. And then to find small q, we need VQ over I. We can calculate capital Q and I using their expressions, and it was very easy. Just remember that capital Q can be found, the first moment of area has to be found for the area which is above the horizontal force. Horizontal force exists at the interface of the two planks, two wooden boards. Okay, I will move towards our next problem, which I have selected for this lecture, is problem 6.6. Problem number 6 from the exercise of chapter number 6. The beam shown is fabricated by connecting two channel shapes and two plates using bolts of 3 by 4 inch diameter, spaced longitudinally every 7.5 inch. Here are two channel sections, this one and this one. They are in the shape of C. They're called channel sections. The standard is 12 into C12 into 20.7. We can find the dimensions and the moment of inertia of this beam from the appendix in the book. There are two plates at the top and at the bottom. They are connected to the channel shapes using bolts, this bolt and this bolt. The diameter of the bolt is given to us. It is 3 by 4 inches. And in the third dimension, longitudinally, the bolts are longitudinally spaced every 7.5 inch. In the direction of the length, there are other bolts, and that is this distance, longitudinal distance, is 7.5 inch. Determine the average shearing stress in the bolts caused by a shearing force of 25 kilopounds parallel to the y-axis. Parallel to the y-axis, we have a shearing force, vertical shearing force, because y is in vertical direction. It is 25 kilopounds. And we have to find shearing stress in the bolt. So, parallel to the area of the bolt will be shearing stress. This top bolt will be equal to horizontal, this is horizontal force, divided by area of the bolt. So there are two horizontal forces between the interface of this plate, top plate, and the channel section. Here is another bolt. Here will be another shearing force. Okay. To find top bolt, we need to find H and area of the bolt. Area of the bolt can be found from the diameter of the bolt, and H, horizontal force, is equal to V Q over I T. Okay. Sorry, V Q over I. V Q over I into S. S is this longitudinal distance, longitudinal spacing. V is given to us, S is given to us, Q and I have to be found. I of this whole cross section can be found by adding I of the channel section plus I of the plates. Because there are two plates and two channel sections, so I have multiplied it with 2. And Q is equal to A into Y dash, which A we have to use the area above the horizontal force. Horizontal force exists between the interface of the plate and the channel section. So area above it is area of the plate. So we'll use area of the plate here, and its Y dash is distance of its centroid from the centroid of the total cross section. Okay. C12 means the height of the C section is 12 inches. This total height of the C section is 12 inches. So it means half of it is 6 inches. So this distance is 6 inches. So Y dash is equal to 6 plus half of the plate thickness. Plate is 16 inch into half inch. 16 is its length and half is its width. So half of the half inch is 0.25. It becomes 6.25 inches. Y dash. Area of the plate is 16 into half inch. 16 is its length and half inch is its width. So we will go towards the solution. I 6.6. I can be calculated using this expression 2 times I for C section plus I for plate. Okay. I for the C section can be calculated from the appendix. In the appendix, if we go towards appendix C and find go on the page for C sections, C12 into 20.7, here we can find IX. It is placed in this orientation where X is the horizontal axis. So IX is 129 inch power 4. So 2 into IX plus I of the plate. The plates are actually not lying on the centroid of the beam cross section. So we have to have its value of D, AD square, area of the plate into D. D of the plate is again this equal to this Y dash is 6.25. So it is BH cube by 12. Our width of the plate, height of the plate divided by 12 plus area of the plate into D of the plate square. So I will put the values here. 2 into 129. 129 was the value of I for the C section. This one. Plus width of the plate is 16. Height of the plate is 0.5. Cube divided by 12. Area of the plate is 16 into 0.5. 16 is width and 0.5 is height. And D is 6.25. So by simplifying this one, I becomes 883.33 inch power 4. Okay, for Q is equal to AY dash. Area of the plate into Y dash. Area of the plate is 16 into 1.5. Why we are using this area? This area is the area above the horizontal shear force line. Horizontal shear force exists on the interface of C section and the plate. So above this, the area of plate is 16 into 16 into half inch, and Y dash is 6.25 inches. 16 into half and Y dash is 6.25. So Q will be 50 cubic inch. Okay, we have calculated Q as well. Area of the bolt is equal to pi by 4 into diameter of the bolt square 3.1416 divided by 4. Diameter of the bolt is 3 by 4. It is given to us in the problem statement. So area of the bolt becomes 0.44179 inch square. Okay, everything is known to us. Now we need to calculate small q, which is equal to VQ over R. V is given to us, it is 25 kilopounds. Capital K has been calculated as 50 cubic inch, and I has been calculated as 833.73 inch power 4. So small q becomes 1.415 kilopounds. From the small q we can find horizontal force. Horizontal force is equal to, because we have two bolts, so horizontal 2 times horizontal force in the bolt is equal to Q into S. Q is known to us, it is 1.415, and S was given in the problem statement, and I think it is 7.5 inches. Longitudinal spacing. Okay. S is 7.5. H bolt, horizontal force horizontal force in the bolt will be 5.306 kilograms in each bolt. This is horizontal force in each bolt. So stress in bolt will be force in the bolt divided by area of the bolt. And stress in the bolt is 5.306 kilopounds and area of the bolt is 0.44179. The top bolt is equal to, it comes out to be 12.01 kilopounds per square inch. The stress in the bolt has been calculated. I hope this was a very simple problem. We just needed to find horizontal force in the bolt. Area of the bolt can be found from its diameter, and horizontal force, because there are two bolts, there will be double force. It is equal to Q into S, and Q can be found from V, Q or I. In this problem, the main important thing was to find Q and I, capital Q and I. The capital Q is A into Y dash, area above the horizontal shear force, and Y dash is distance of centroid of that area from centroid of the total cross section, and I is moment of inertia from the whole cross section. Okay, we will move towards our next problem. The next problem which I have selected for this lecture is problem 635 from the exercise. An extruded aluminum beam has a cross section shown. Knowing that the vertical force in the beam is 150 kilonewton, this is cross section of the beam given in the diagram. Vertical shear force V is given to us. It is 150 kilonewton. Determine the shearing stress at point A and point B. This is a thin section. Vertical shear force V is 150 kilonewtons, and the vertical force enters at this point in the box section. It is a box section, and then it is divided into two streams. Like this. Okay, we have to find shearing stress at point A and at point B. Okay, for this we need small q first, because shearing stress is equal to Q into T. Shearing stress is equal to Q over T. For thin sections, it is Q over T, or VQ over I to T. V is given to us. We need capital Q and I and T, thickness. Okay, capital I is same for the whole cross section. Capital Q and T are different for the 2 points A and B. For point B, it lies on this section. Thickness is 6. T is 6. TB is 6. And TA is 12. A lies on this part. Okay. When the shear flow starts from here, where it is 0, and it reaches till point B, it covers only this area. So for point B, when we calculate capital Q, for point B, it will be this area into Y dash. Its distance from its centroid. Distance from its centroid will be this one, YB. And for A, point A, when shear flow starts from this point, it will cover this whole area, and then it will reach point A. So it consists of two areas, AB plus this area, AA. I will divide it into two areas. This new area will be added. So QA is equal to AB to YB plus AA to YA. This extra area has been added to it. Okay, some people consider both this part as well, this section as well. Then you have to take double thickness in this case. I am just considering half of the part when the shear flow starts from here and it moves from B till A. It passes from B and then reaches till A. Okay. I will move towards its solution. Problem 6.35. The box section like this. Point B lies here and point A lies here. This width is 150 mm. All the dimensions are in millimeters. Height is 80 and thickness is 6 and 12. Height is 80. Thickness of this part is 6 mm and thickness of this part is 12 mm. Okay, I is equal to I of the outer portion minus I of the inner portion. So B outer, H outer cube divided by 12 minus B inner, H inner cube divided by 12. B outer is 150. Height of outer section is 80 divided by 12. B of inner section is 150 minus 12 minus 12 because 112 is here. Thickness here is 12 and the other part is also 12. So it becomes 150 minus 12 minus 12. It is 126. Height, total height is 80 minus 6 minus 6 becomes 68. So outer rectangle minus inner rectangle. So I becomes 3.098 into 10 power 6 mm power 4, or it can be 3.098 into 10 power minus 6 meter power 4 by keeping 1 millimeter equal to 10 power minus 3 meters. Okay, I has been calculated. For capital Q, first we consider if this is the midpoint, small q starts from here. We are considering this area. This is AB and distance of its centroid is YB. Okay. QB is equal to AB into YB. What is AB? For the red highlighted portion, the width is 126 and the thickness is 6. And YB is equal to distance of centroid of this area AB from the centroid of the total cross section. The total height is 80. Half of the height is 40. If we subtract half of this thickness, 6, half of this thickness 6 is 3. If we subtract 3 from 3 from 40, it becomes 37. So y dash is 37. So QB becomes 27.972 into 10 power 3 millimeter cubes, or in meter cubes it will be 27.972 into 10 power minus 6 meter cube. Okay, QA. When the shear flow starts from this point and it reaches at point A, it covers area AB and then this area as well, this vertical area till this point. So shear flow starts from here and it reaches till point A. Okay, so this area in blue color needs to be found. The previous one has already been found. I will find this area, and centroid of this area, from the centroid of the total cross section, is YA. This area is area A. So QA includes both area AB and AA and YA and YB. So it is equal to AB YB plus AA YA, because the flow has to start from the starting point and it has to reach at point A by passing through point B. So it includes AB as well. Okay. The first part is already known to us, AB and YB. It is already equal to this value, 27.972 into 10 power 3 plus AA, area of the vertical portion in the blue color. It is equal to its thickness 12 and half of the total height, which is 40. 12 into 40. Into 40. Sorry, before this I want to make some correction. This QB has some problem. There's some correction which I need to do. This is not 126, it is half of the 126. There is some mistake in our calculation. It is 63. This width is 63. Okay, so I will make a correction. 27 point, this becomes 13 point 13.986 okay, sorry for the mistake. Okay, AA is equal to 12 into 40 and YA is half of 40. Height from the midpoint till the outer section is 40, so YA is equal to half of 40, it is 20. So after simplification, QA becomes, if we do the calculations, is 20.586 into 10 to the power 3 millimeter cubes, and if we want to convert it into meter cube, it will be 20.586 into 10 to the power minus 6 meter cube. Okay, QA and QB both have been calculated. Now we can find stresses at point A and point B. Thickness at point A is equal to 12 mm and thickness at point B is equal to 6 mm. So TA and TB are also known to us. TB is 6 mm and TA is 12 mm. Now we will find stress at A and stress at B. Stress at A is equal to VQA over ITA. V is given to us 150 kilonewton, 150 into 10 power 3 newtons. QA is 20.586 into 10 power minus 6. 20.586 into 10 power minus 6. I is known to us. I is 3.098 into 10 power minus 6. And TA is 12. 12 mm means 0.012 meters. Tau A becomes, shear stress at point A becomes 95.2 into 10 power 6 pascals or 95.2 megapascals. Similarly, tau B, shear stress at point B, V into QB divided by I TV, 150 into 10 power 3. QB is 13.986 into 10 power minus 6. IB is 3.098 to 10 power minus 6, and thickness at B was 6 mm or 0.006 meters. So tau B will be, after calculations, it will be 112.844 into 10 power 6 pascals or 112.8 megapascals. Okay. So shear stress at point A and at point B have been calculated. This was needed in the problem statement. The important thing is to find Q and thickness for both the parts separately. For Q, it is you need to be very careful. You need to consider the correct area. In this case, we always start from this midpoint, and the shear flows like this. It passes from B and reaches point A. So for B, we need only this red portion area, and for A, we need red plus the blue area. Some people consider this section as well, this whole area. Then they have to multiply thickness with 2, because then they consider these 2 thicknesses. I have considered just half of the portion, which is the real flow portion, so I have considered the real areas. Okay, I will move towards the next problem, which is problem number 638. I have chosen this problem for this lecture. The vertical shear is 1200 pounds in a beam having a cross section shown. Knowing that D is equal to 4 inches, determine the shearing stress at point A and point B. Vertical shear force is given to us, V. This D is equal to 4 inches. This is also 4 inches. We have to find stress at point B and point A. I have chosen this problem specifically in the context of previous problem. It was a box section. This one is an I section. They both are thin wall sections. In this case, shear flow starts from this point and at this point simultaneously, and then they add up together add it up together. So if this is Q1, this is Q2, so this Q is equal to Q1 plus Q2. But if this is Q1, this is also Q1. If this is Q1, this is Q1. Here is this portion is Q1 plus Q2. If this is Q2, so at point A, it will be Q1 plus Q2. Okay. When we find shear stress at point B, we have to consider this area because flow starts from here and it moves and reaches point B. So I will consider just this highlighted area. If I have to find shear stress at point A, so then the flow at A needs to consider this whole area because the shear flow starting from this right end and left end, it merges at the mid and it is included the whole area. So when we have to find shear stress at point A, we have to consider this whole highlighted area, and when considering about B only, so we will consider only this area. Before that, we will find I. The method is same as the previous problem. Before this, we have to find I. So I for the middle portion plus 4 times I of this part. Okay, I will move towards the solution. Problem 638. Here is a diagram. This is 5 inches. Is this in inches? Yes, 5 inches. This is 4 inches. Thickness of this portion is 0.5 inch. And this is given to us okay, the total height is 8 inches. This total height is okay, we have to find I of the 4 portions is equal to 4 times 4 into 0.5 cube divided by 12 plus AD square, because these 4 portions do not lie on the cross section, so their area 4 into 0.5 into D 3.75 square. I hope you can do it. How to find this D plus I of this middle portion. 5 into 8 cube divided by 12, and its cross section lies on the cross section of the whole. Its centroid lies on the cross section of the centroid of the whole cross section. Total I becomes 326 inch power 4. Okay. Now I will find this is point B, and here at the mid is point A. First I will find QB. QB is equal to area until point B into voltage to point. Area until point B is this area. Is 4 into 0.5 inches. 4 into 0.5 inches multiplied by YB. What is its distance of its centroid from centroid of the cross section? This is 3.75. Total height is 4 from the mid, and by subtracting half of this width, it is 3.75. So QB becomes 7.5 cubic inch. And TB, thickness of the portion at point B, this thickness is 0.5. Okay, similarly QA it includes already highlighted area, this area plus this area plus this blue area. So the area highlighted in red color is already the same area which we have used for QB. So there are two portions in the red color. So we will use 2 times area B YB plus this portion in the blue color is single area. This area is equal to 5 inch into 4 inch, 5 inches into 4 inches, 2 times the previous value, which is 7.5, plus area A is 4 into 5, and YA, its centroid from the total centroid, it is 4 divided by 2, it is 2. Okay, so QA becomes 55 cubic inch, and thickness at A, thickness of this portion, it is 5 inches that A exists. Now TA is known to us, TB is known to us, V is known to us, and I is known to us. So shear stress at A is equal to V QA over I TA. V is given to us in the problem. It was 1200 pounds. 1200. QA is 55 cubic inch. I is equal to, I is moment of inertia of the whole cross section. It is 326 inch power 4. And TA is 5. So tau at A is 40.5 pound per square inch. And tau at B is equal to V QB divided by I TB. V is 1200. QB has been calculated as 7.5 cubic inch. I is 326, and thickness at B is 0.5 inches. So it will be 55.2 psi. So tau A and tau B, shear stress at A and B, have been calculated using the formula VQ over IT. So QA and QB were very important. We need to know the exact area. For point B, it was this area, this one. And for point A, it was the area with red color plus the area with the blue color shading. If we know how the shear flows in a section, in an I section, it starts from this point and it grows and merges and reaches the centroid A. For the box section in the previous problem, we have discussed it starts from the midpoint and then it splits in the two directions. Whichever point is asked, we just need to consider area from the 0 till that point. I hope it was understandable. If there is any question you want to ask regarding the solution of this chapter or any other chapter or any other concept related to mechanics of materials, you can send me an email and I will try to answer. Thank you very much.